It's amazing to me to think that spacecraft have actually gone to the surface of Venus and taken pictures. And the environment there is horrible. We always talk about how it's hot enough to melt lead, that the pressures are the equivalent of being under the ocean at a kilometer, and there's sulfuric acid that's trying to eat in. And it's sort of surprising that landers have survived at all, but the Soviets pulled it off. But they didn't last long, just a few minutes. So what would it take to send some kind of lander to the surface of Venus that could survive for not minutes, but maybe days, months, maybe even indefinitely? So my guest today is Dr. Tibor Kremic, who works at NASA Glenn Research Center, and he and his team are working on electronics, batteries, other components of a spacecraft that are designed not only to survive at high temperature, but to really function, to thrive in temperatures that are that hot and under those kinds of pressure and corrosive chemical conditions as well. So we talk about the different kinds of electronics, battery systems, and other ideas to have a much longer exploration from the surface of Venus. All right, here's the interview. Does our imagination let us properly appreciate just how awful it is down at the surface of Venus?
Well, some people that with really exciting imaginations probably can. Right. I think it's really hard. I think it's really hard to appreciate how challenging it is.
Yeah, like when you look at Venus, like when you look at pictures of the surface of Venus, even the ones taken by the Venera spacecraft, it looks like you're, I don't know, like near a volcano. The sky is sort of orangey yellow and cloudy, and the rocks look like they're covered in sulfur, but it's far worse than that, right?
Well, that's a great description. I mean, it's kind of eerie, like you're in an oven where everything's around you is just hot. I mean, it gives you that sense. It is worse than that in terms of the pressure part. So that scene doesn't really reflect the intense pressure that one sees. Also, there's I think some challenges that people don't appreciate as you get to the surface itself, coming from space, very cold. You're going very quickly through, well, not so quickly, through a sulfuric acid bath, if you will, through the clouds. And then it just gets hot and really dense and high pressure. And then you described it well on the surface. It's like a orange mist, kind of very thick. You don't really see very well. You can't like pinpoint where the sun would be. It's all very diffuse. So just kind of a fuzzy red glow, orange glow, and it's hot.
Right. Yeah. And I mean, I love this story. When you think about, say, the Soviets attempting to land on Venus with their Venera program, it was all about like each probe they made a little tougher and then learned where it failed. And then until finally they were able to reach the ground. But they had no idea what environment they were going into. They just knew that they hadn't built their last spacecraft tough enough until they finally did.
Yes.
And yet with the Venera program, we only got less than an hour of observations from the surface of Venus. So what will it take to be able to have something last on the surface of Venus for a longer period of time?
Yeah, that's a great question. And so, like you said, there have been many attempts, right, to put down very large, sophisticated, heavy platforms on the surface of Venus, and minutes, right, and that it lasts, right. All that investment, all that energy, all that money, it just only lasts for a few minutes. Wonderful science, still wonderful to take some of those measurements. A lot can be done, but that's not what we're trying to do here. What we're trying to do, instead of trying to control this really nasty environment around us, and really doing that without a way to harness power or energy out of the system, what we're trying to do is make ourselves and design it so that we're happy living in that nasty environment. That's really our approach. So we're putting away the large, the big, the heavy, and trying to control our thermal environment. Rather, we're going from the other direction. We're leveraging investments and years of work that we've done in high temperature electronics, sensors, and to build a system that will be happy in that nasty environment. And that's our approach. And if you can do that with the appropriate power system, that's how you can attain weeks and months of life on the surface of Venus.
So then break that down for me. Like if you were looking at it from the conditions of Venus, where would a traditional spacecraft fail, and what are the pieces that you then have to re-engineer?
Yeah, so the Achilles heel of spacecraft of Venus is primarily the temperature. So, and the temperature, so we can make vessels that keep out the pressure, and many of our systems that we take there aren't really susceptible to pressure, but they are susceptible to temperature. So what happens is that, and it's primarily the electronics, right? So we send this vessel down. The way the Soviets have done it is they had this giant pressure vessel, and they had phase change material. So that would keep the temperature at a max for, like you said, minutes, right? Until it soaks in all that heat. And eventually that phase change material expires, if you will. All the energy it can absorb is gone. And then the temperature inside starts to rise. And then when it hits the limitations of the electronics, that's when things stop operating, and that's when the life ends. So that's really what kills spacecraft. It's the temperature of the capability of the electronics to sustain and operate in those conditions.
Right. Your solder is melting. Your batteries are frying. Every part of the spacecraft electronics is designed to work at, room temperature-ish on Earth, not that.
Right.
Yeah.
That's correct. That's exactly right. And even some of what we call high temperature on Earth are nowhere near the 460 degrees that Venus is at. So high temperature electronics, you might say 200 degrees C or something like that. We're at 460 on the surface of Venus. So quite a bit of a gap there between what we can do with traditional terrestrial electronics and what has to work on Venus.
Right. Okay. So then explain then the process. What are the technologies that can swap out some of the more vulnerable parts into something that can handle that high temperature environment?
Yeah, so the key that we're leveraging is, like I said, decades of investment in silicon carbide based electronics. So it's not silicon, it's a wider band gap. So the energy levels to move things around in the electronics are higher. And that allows us to, and that technique and deliberately designing for robust systems. So looking very carefully at how systems fail at those temperatures over time, right? And then adjusting the fabrication of the internal designs of the ICs and so forth, using these materials that are specialized and can endure not only the temperatures, but also some of the chemical things. So one of the things we haven't talked about is the chemistry at the surface is also not very friendly. So it's reactive. And so when it doesn't matter if you're going to be there for a few minutes, but as you're talking about weeks and months, you have to be compatible with that reactive chemistry. And so those are all the pieces that we're working on. So, but primarily it's leveraging the silicon carbide based electronics that have the ability to operate. And we've demonstrated operation of those types of electronics for thousands of hours at 500 or more degrees C.
So you can take a silicon carbide microchip and run it in 500 Celsius for long periods of time with no detrimental effects.
That's correct.
Right.
That's exactly correct. Now, one thing I would point out is that the sophistication and level of these electronics are not what we're accustomed to in our terrestrial electronics. So, it won't have the power of our smartphones, for example. It's simpler electronics. Think back in some of the early space missions. That's the fidelity. That's the capabilities that these types of electronics can handle today. But of course, we've invested effort, and we're continuing to invest effort to make those become smaller, make them be able to do more processing, more complex, and allow us to eventually get to that level of sophistication. But that'll be a little bit farther down the road.
Right.
Our first generation won't be at that power level.
Right. So you can't go to Intel and request a silicon carbide version of the i7.
No.
Right.
No. I mean, you can go there, but you're not going to get anywhere.
You don't get anywhere. They don't have a chip fab set up for that. So then, give me an idea. You say the sophistication of these early spacecraft. So essentially, you are creating your own chips with the materials that you have available, but with this other kind of chemistry. So what is it about silicon carbide that provides that temperature protection?
It's the wide band gap. It's the energy levels and then the materials that are in there that allow it to operate at those higher temperatures.
And or how
the ceramic kind. Yeah, go ahead.
And theoretically, let's say you could convince Intel to go and redesign their chip fabs. would you be able to see performance out of silicon carbide that would match existing silicon chips, or is there some kind of like fundamental lack of performance just coming from that material?
Well, there's a fundamental difference. So I'm not probably the best one to predict how closely one can get to, but there are physics-driven things. The transport of electrons and so forth are different. The architecture. So an IC chip can be developed using different types of electronic transistors, different types of transistors and components that can create that. So most of our electronics right now are based on the field effect transistors. So JFETs is basically the architecture, the transistor architecture that we're using. So those have certain features that are different from bipolar junction transistors, for example, and so on. So it's a deeper kind of question than what the IC itself can do. It's really the nature of the pieces that you make that up with, and each of those have features. So some of them, for example, because of the electronics, the JFET architecture we're using, that has a certain power consumption characteristics. It also has limitations on how quickly one can switch from one state to another. And so as we look to increase our, for example, communication frequencies, we're going to have to move away from the JFET architecture and into something else to allow us to get those higher rates of transmission and switching between these devices. So those are examples where I'm trying to convey that, so it's a whole how do I want to say this? There's a whole series of things that have to kind of grow and mature together to be able to reach that level of sophistication.
Right. I mean,
and some of these are different techniques, different devices, and then they all protrude. But there's going to be fundamental differences just by the nature of the materials that we use.
I mean, I'm sure as you look at the capabilities of an existing spacecraft, say you take the DART mission or something else that you've worked on, and you look at all of the off-the-shelf components that you're just relying on the communication systems, on the bus, on the memory architecture, all of that kind of stuff, you can't take any of that for granted anymore. You've got to go and re-architect each one of those pieces using this essentially entirely new ecosystem. And you can't get a giant Intel chip fab working on your behalf. So you're having to replace this functionality. So you lose performance, but I'm guessing what you gain is that it even functions, which is
correct. Absolutely.
Which is the benefit.
Exactly right.
Right.
And you said it very well. It goes across the whole system. So electronics is only one piece of it, right? But there's the power system, there's a communication system. All those have to, like you said, they have to work all of that together and increase the capabilities of all of those to have the system work, because it's like a chain, right? One piece doesn't work. You don't have a power source, nothing's going to happen. You don't have a communication system, you don't get any data back. You don't have electronics, you can't do any processing or take measurements. If you don't have the sensors, you can't get the data off the surface. So all those pieces, like you say, have to work kind of together, and they all have different challenges. So that's really the fun part about this. And this is why, I love what I do.
Yeah,
right?
yeah.
Because we're tackling all of this stuff, and it's really exciting.
Right. And I can just imagine, as you say, you look at all of these pieces and then you go, yeah, but what if it was on Venus? And you'd be like, oh, right, the antenna would melt. Oh, right, the solder would melt as well. So
right.
Let's talk about, we've talked about like the chip side, and it sounds to me like seeing this run in an oven for months on end and still computing happily has got to make you feel confident that piece of the puzzle is now moved into the engineering realm and needs solutions. Let's talk about batteries, because this is sort of what put you onto my radar in the first place. Mm-hmm. Okay. You're working on a battery that can theoretically work in a high temperature environment.
That's correct. So basically what we're doing here is we're leveraging investments made by others in government and industry. They're called thermal batteries. So these are batteries that are designed to sit very comfortably for years and years and years, keep their charge. They're totally inactive, totally dormant. And terrestrially, what has to happen is that they have to be raised to a high temperature, and that's typically done by firing a pyro that's inside the battery itself, so that it can soften up and get the electrochemistry can start to function. right? So on Venus, we've got the opportunity, if you will, to just harness the heat locally. We don't have to fire anything,
Right.
but just let it get hot as it descends. The spacecraft is descending into the environment. And through the atmosphere, and as they get close to the surface, if it gets hot enough, then the electrolytes in there will melt, basically, and it'll start acting as a battery. It'll start generating power.
Wow.
So that's really what's happening here. Is we're taking an Earth application and flipping it over on its head, not putting it into an environment that the battery itself is happy, but we have to modify the chemistry in the internals, because typically the applications here are very high powers for very short time periods. On Venus, we want to do just the opposite. We want to have long periods of operation and just minimize the amount of energy that we're taking out of each time. So there's work to work on. There was work to develop, redevelop the chemistry, if you will, but still keep the feature of it being totally resilient, like a brick, if you will, as it comes in, as it goes, but then it will just turn on and operate for a long period of time on Venus. So that was the approach we took, and that's kind of where it's looking at it's going to happen. And
what are give us a sense of the kind of chemistry or materials that are involved and how they're different from, I guess, a traditional battery, like a lithium battery or zinc.
So I'm not an electrochemist.
Right.
So some of those
broad strokes.
I won't be able to get too much details, but so they're lithium iron sulfide elements, as well as other things. I'd have to go talk to somebody to get the chemistry.
But the point is that you've got a mix of chemicals that it batteries at 450 Celsius on the surface of Venus.
That's correct.
Yeah.
As it gets warmer, we're up well above 300 degrees Celsius. There's a solid electrolyte at lower temperatures that melts at those temperatures, and then it allows for the currents to flow in the chemistries between the cathode, anode, and function of this electrode. And we have multiple cells that are put together to give us the right voltage that our system needs to run those electronics, because they'll also have different power needs than normal electronics. A couple small 5-volt thing won't work for us right now. So all that, again, works as a system together. But we design that battery for the voltage that it has to produce, the pressures that it has to take, and also the chemistry that has to live in. Again, we're always mindful that we're in a reactive chemistry. So we have to pick. So copper and things like that we typically use on spacecraft are not going to work on Venus.
And so you would, I don't even know how you would describe it, but you would charge it up here on Earth almost by, putting in the right metals or maybe heating them up and then charging it up. And then you would let it solidify and then send it to Venus. And then as it melted, it would have that power differential between the cathode and the anode, and it would be able to actually start functioning as a battery. Do you have a sense of how long the battery would last?
Yes, so that's really what we've been working on, is to make sure that the battery itself doesn't erode its own energy because of the things that are going inside the battery. So self-discharging, we minimize the self-discharge. After that, it's really a function of how we're drawing energy out of it. So we'll have a certain amount of watt hours, certain amount of energy that's in that battery. Over time, that's going to slowly deplete because there is some self-discharging. But if that's low enough, then it's really a function of how we choose to take the energy out of it. And that's another feature of what we're trying to do, is that we are not we're focusing on the type of science that's really uniquely aligned with what we can do, the long life on the surface of Venus. So that's never been done before, taking time-based measurements, things like weather, for example.
Right.
Try to imagine, you put a lander that lasts for a few minutes on the surface and then trying to predict what the weather, the climate is like on Venus. It's going to be really tough to do, right? So we're trying to focus on science that you can do uniquely with the fact that you're there for long periods of time. So we've taken time-based temperature measurements, pressure measurements, wind measurements, energy deposition. So how much energy from the sun actually gets down to the surface. Those are the types of things we do. So what we do is, the way we operate this is that those types of measurements don't require very high frequency measurements. So we don't have to take 10 samples of temperature a second, where we know that over a whole Venus day, it's only going to vary 2 or 3 degrees Celsius, right? So we're going to, basically keep track of time most of our mission, and then periodically, let's say maybe every 8 hours, we'll take readings. We'll take readings of all our sensors and transmit them, and then we'll go to sleep so that we can extend the time that we can stay alive on the surface. So by doing that process, we expect, and we're designing for being able to operate for 60 days on the surface of Venus with larger batteries. We can double or triple. That depends on how much battery mass we want to take. That's where most of our mass goes to, in fact, is the battery.
And so you could provide, I guess, intermittent weather measurements over the course of 60 days from this, which is long enough to get a sense of what the weather is like on Venus. Because right now, the assumption is that it's always hot, but who knows if it's
that's
slight
correct.
Variations in hot.
Slight variations in hot, but there's also the timing of this. The 60 days was really targeted from a science perspective. So the Venus solar day is, so Venus rotates every 243 days. It's solar day because it's spinning backwards is twice that, right? So if we have a mission for 60 days, what that does is it guarantees us we go from a day to a night or a night to a day transition somewhere in there. And that's never been measured. Mm-hmm. So we don't, so I don't know if you're familiar with the super rotation, the
winds,
velocity winds up in the upper clouds. And so we don't really still understand what drives that. We have some theories and ideas, but we don't really know. Some of the key is what's happening at the surface, right? And so our ability to take measurements across that transition may really help inform the global weather, the global climate, the global atmospheric dynamics of the system. And so we've targeted our 60 days to make sure no matter when we land, we're going to capture one of those events.
And what about being able to analyze the chemistry of the atmosphere as well? I mean, I know that, we don't really understand if there's volcanism on Venus, active volcanism. Would you be able to analyze the chemistry of the atmosphere and be able to give a sense of what's going on there?
Yes, in fact, that is one of the we have a chemical sensor suite, and what it does is it uses MEMS devices, and for certain species. So it's not like a mass spectrometer where we ingest and then look at what's there. What we do is we have tuned MEMS sensors that look at abundances of certain species, things that we expect to have on the Venus, near the Venus surface. And we use those. These are very small, low power devices. And we do, just like with our weather measurements, we take those. And so we're measuring chemical abundance variance over time for those selected species. So we are doing that. And that's another measurement we can take with very low power, low data volume types of measurements, what we can do over time. And like you say, if there's some outgassing, if we're by a volcano, is it spewing out SO2? Is what's happening? Those things we would be able to detect.
What about moving? I mean, when you look at Mars, exploration of Mars, I mean, the rovers have revolutionized what we're able to find traveling from place to place. But I'm sure with that, you need better communication to and from the spacecraft, some kind of camera system. Like, it starts to get complicated fast. Have you thought about what it might take to build a rover?
We have actually. We've pulled together a team of experts from around the country not that long ago, and we looked at basically surface platforms. What sort of science could you achieve with different capabilities? Mobility is one of those. If you had mobility, you can do certain things. If you had a lot more intelligence, processing power, higher fidelity electronics, you can do other things. And so we've looked at, if you had more time, you can do more things, right? So we have looked at rovers. I think, and personally, the hardest challenge with rovers on the surface of Venus is a power system. If you had enough power, you can control your thermal environment. Some of those things are really difficult to do in those conditions. Those are the things you'd really focus on, and to use some of the terrestrial capabilities and invest in the cooling. So power is a key for some of these, and mobility, of course, needs higher power than you typically have with a battery, right? At least not for a long mission. So you would need something different, and that's the key there. A high temperature power system that has long life. And that would give you the ability to do mobility.
And the assumption that I guess we're making in the beginning is that this battery is being sent to Venus fully charged, and then it's going to discharge over the course of its mission.
Correct.
Is there any way to get energy into it from the surface of Venus?
Yeah, that's a great question. So we've been looking at that too. So there are two candidates for that at the moment that we've noted. One of them, there is solar energy that does get to the surface. It's much lower than here on Earth, even though it's closer to the sun. But because of those thick cloud layers and a very dense atmosphere, not much of it actually gets to the surface. So and then the temperatures also will make a system that captures solar energy, converts it to electrical, very inefficient. So you need large areas for very little power. So, but that could be enough to trickle charge, for example, a battery, recharge a battery. So that's one. Another one is winds. So the missions that have gone to the surface of Venus have detected surface wind speeds. They all read somewhere between a quarter to about 1.5 meters per second as the velocities of those. So one can imagine maybe harnessing some of that with some sort of windmill. So we have designs and thought and some concepts of how to do that. Again, unless you're taking a very large system, it's going to be small amounts of power. So the velocities are low, even though it's very dense. So that's a good thing, but the velocities are very low. So you get minimal energy that you can take out of that. The thing with the wind one is that we don't have enough measurements to be real confident as to if we're going to have wind at the spot we land and how persistent and consistent is it. And so I think we're going to have to take some of these early measurements, like with what we're doing now, measure the winds, and then in the future we can design some systems that can maybe take advantage of some of that. So right now the battery seems like the best thing to do initially.
I know there's some research by NASA a few years ago into looking into non-electronic forms of rovers, clockwork rovers that could explore the surface of Mars.
Correct.
Has any of those ideas sort of continued on into the work that you're doing?
Well, I'm not the one to comment on how those have progressed. I do know some of the people that have developed those, and we've interacted with them. So they have done some work. I don't know how this is progressing today, so I can't really answer that question. What I can say, though, is that I think in the long term, we'd probably want to be working together with some of those capabilities and those ideas, along with some of the very focused ones that maybe we have. So if you have those types of rovers, that's really wonderful. You're still going to want to get the data off and somehow transmit it to an orbiter or back to Earth. And so some of those techniques are hard to see how that's viable right now. So there's still maybe some elements of those types of rovers, even though you can find mechanical ways to keep track of time or move and mobility and all kinds of things. There might be some combination that might be the best if we work together on that. So that's my personal view on that, but I don't know where they're at.
Yeah, the methods of communication mechanically were actually my favorites of the whole system.
Yeah.
Because they would do things like have like retroreflectors that are spinning around and they can mechanically change. And so you could view from orbit a configuration of retroreflectors on the top of the rover, and you would use that to transmit information as an orbiter is flying past, since you wouldn't necessarily need to have
So like a radar reflector?
Yeah, exactly. Yeah, you would have a radar reflector on the top of it, and you would be able to kind of open and close some kind of dot matrix on top of the spacecraft. And then as your orbiter flew overhead, it would measure that and go, okay, that's the weather, that's the temperature, whatever, and keep moving and save yourself all of the power of the transmitter. So actually, when I was keeping track of those science papers, I mean, the strand beasts concept was great, but I really suspect that it's going to be that communication is going to be power hungry. How do you get that information from the surface of Venus through that horrible atmosphere and back home to Earth?
Right. That is the big energy draw. Yeah. So let me ask you a question then. So I haven't followed this. So in terms of the measurements themselves, so they have a so the mechanical approaches, they have a way to mechanically capture temperature or some data and then transfer that mechanically to this indicator?
Yeah, yes. That you would have some kind of mechanical version of a thermometer that would based on the temperature that it was reading, it would change it would open up a different configuration of radio reflectors, radar reflectors on the top of the rover that would then be read by something from space, like Braille almost. But I think that in your situation, obviously, you can skip all that and just go straight to configuring the reflectors electronically. So I suspect that there's a lot of really great ideas to solve some of those problems. So there was another, I think it was a NIAC grant a couple of years ago about a wind sail, something that would
I'm familiar with that,
like
one,
a land sail that would just slowly drift across. It
had solar panels for the sail itself,
right,
or on the sail itself. I've seen that one.
I wonder, like, you talk about that idea of solar panels, but I think you're probably back to that same issue, right? That you have to, like, a solar panel is a computer chip, and so you would need to re-engineer. And so do you feel pretty confident that you can make solar panels out of these silicon carbide chips?
So that's not work that we're doing here, but so there are people. I'm trying to blank on his name. Jonathan is his first name. Grandidier, I think, is who the principal investigator was for some NASA awarded activity to develop a high temperature solar cell. So yes, there's been some work. There's been some promising work on that. We're not working on that right now here, but we have talked to them because, as I mentioned to you, the trickle charging. So one of our life limiting things is the most of the power goes into the communication system, as you mentioned. That's where the energy goes. But the second thing that actually takes the energy is the keeping track of time, because we're using an electronic system for that. So even though it's very low, but it's always on. And so if we can come up with a recharging system, if you will, maybe with solar cells, that makes up that difference, then our life can really grow quite significantly, right? So then it's really, we still have to, especially if we have something above that, right? We can slowly recharge, and if we set our frequency of communications equal to the energy that it takes that to the energy recharge with, we can potentially go indefinitely.
Right.
So those are things that we're looking at.
Right. So in the beginning, you're checking every couple of hours, and then you start checking every couple of days, and then every couple of months, and you're looking for those much longer seasonal patterns. As long as you can stay ahead of the power drain, you could last until, I guess, the corrosive atmosphere dismantles it at an atomic level. Well, that's right. We'll have to build a thing so that the corrosion doesn't happen either. We'll select our materials that it doesn't happen. But that's where something like a solar cell, high temperature, could really play into the system, and why we've been talking to them about those kinds of things. What are the areas that are necessary? How big are we? If we make it too big, then of course, then it's difficult to land and integrate into other vehicles. And if it's too small, then we won't get enough power. So those are all the kinds of trades that we continue to do. So this is going to sound really weird, but are there any advantages to Venus? Like NASA is planning on sending this helicopter to Titan. Titan's another very inhospitable environment, and yet it has a low gravity and a thick atmosphere that allows a helicopter to function actually quite nicely. Is there anything that Venus has going for it with all of this sort of horrible environment?
Oh, well, so what's the motivation for going to Venus? And there's a whole bunch of them, right? Beyond the obvious, it's a mysterious place, and we want to explore and we want to find out. But a little bit more deliberate, more deeper than that. So Venus is, our closest neighbor, right? It's the planet that's closest to us. It's very similar in size. The mass is very similar, probably made of the same materials and so forth. The composition is similar. So why are they so different, right? And so the thinking is that there's probably more Venuses out there than there are Earths. And so when we look at planets around other stars, when we look at our planet, what can we learn? And so Venus could tell us a lot, right? Trying to solve these mysteries will tell us a lot about our solar system, about Earth, and about other planets around stars. So all these mysteries, like, why do you have the super rotation? Why is Venus spinning so doggone slow and backwards? What's going on with the magnetic field that we can't find? What does that tell us about the interior? So there's the other simple kind of fun things to think about. Venus's day is longer than its year, and and no seasons, all these things. So, and the super rotation. So there's a whole boatload. Not even getting into some of the atmospheric things that are quite unique. The UV absorber, which you probably heard about, detection of phosphine and something. So all kinds of things about Venus, that it's a laboratory for us to learn about ourselves and about other bodies. So there's a lot of compelling reasons to go to Venus.
Yeah, and I love that idea that Venus, I mean, is another planet. It's an Earth-sized world with an Earth-sized Earth amount of mass, with Earth gravity in the habitable zone of the sun, and yet we can tell it is not habitable to Earth life. And so how fortunate we are that we have an Earth analog right here with us in the solar system. But then you think about how difficult it is for us to even analyze Venus, and it's right over there. And then we think about the search that we're trying to conduct for extrasolar planets, which are tens of light years away. It shows us the scale of the challenge that we face. Mm-hmm. But I guess and
it shows us the potential of what we can learn by exploring Venus too.
Yeah, absolutely. And I guess what I was getting at, not necessarily from a why go to Venus, but more of the engineering challenges. Are there any advantages to Venus itself? Does it despite all of its sort of horrible conditions, is actually giving us any benefits in terms of making some aspect of the engineering a little easier?
I don't know if they make the engineering easier, but I think there are benefits. So whenever we tackle these difficult challenges, there are benefits to our understanding of physics, and the things that we're developing for Venus will help us here. So there are Venus-like applications here on Earth. Deep mining, for example. So the temperatures and conditions are not all that dissimilar in some situations on Earth. And so the advancements we're making in terms of the sensors, the ability to process, to understand what's going on, will allow us to be more efficient, smarter at the things that we're doing here. So there are terrestrial reasons to do and benefits that we get by tackling these engineering challenges. Making combustion engines more efficient, being smarter about those, taking measurements in places closer to where the action is, allows us to do those things better. So there's all kinds of things, some of which I don't even think we have an idea of how much it can impact in a good way our life here. So I think when we tackle and we overcome some of these challenges, sometimes we don't know yet even all the benefits that that's going to have later, because we just never thought about it. So
yeah, and I think about deep rock geothermal power, where you're going down to the point where your traditional electronics are going to start melting. If you want to analyze the state of the borehole, having a computer that can handle that kind of high temperature sounds like an advantage. But being down on the surface of Venus has been described as being under the ocean, under a kilometer of water and that pressure. And yet, if you're at the bottom of the ocean, things would float. So are there, I guess, do balloons work, dirigibles, zeppelins, inflatable bouncy castles? Is there some strategy that would actually work quite well down near the surface of Venus in terms of mobility and getting around?
Yeah, that's a great question. So that is actually one of the things that, again, we looked at when we're talking about exploring the surface, are using. So instead of driving around, because when you think about it, and you get closer into the details of the Venus surface, a large chunk of it is very similar, kind of flat. So what we like to explore are transitions, where change is happening, or go from one type of surface to another type of surface. And that tells us more than a big area of the same, right? So on Venus, we'd have to go a very long way. Our mobility on Mars, that's not probably good enough for the type of mobility we would need on Venus. So you just pointed out one of the ways that you get around that is by using the atmosphere that's moving above you, and then using some sort of floating platform, right? Some sort of balloon-based system to move around. And there've been studies about that. So as you get higher in altitude, the temperature becomes more Earth-like, right? So there are conditions where you're in the clouds, so you've got your sulfuric acid problem, but your temperature and your pressure conditions are what you're used to dealing with. So there are balloon concepts. Of course, the Soviets have flown balloons in the past as well. There are NASA concepts for balloons, both ones that just float, ones that can control their altitude, different techniques for doing that, and even some concepts where they go down and can touch the surface somewhere, go back up, and then come back down. That could reduce some of the technical challenges if you're only down at the surface for short periods of time, and you use the atmosphere to your advantage to move somewhere else. So there are those kinds of ideas. To really understand a complex system like Venus, we probably need elements of all of these. We need time on the surface at those temperatures to probe the interior, to probe deeper into the chemistry, get below the weathering layer that's on the chemically weathered layer that's on the surface, and maybe alien weather too. But then again, spend time in situ in the clouds and all these things to get a better picture of the whole systems. So I think all of those are factors, and all of those are techniques and tactics we can use to get a better picture.
Yeah, it is interesting. Like, philosophically, for the longest time, we've been quite fixated on Mars, on the habitability of Mars. Was there water on Mars? Is there life on Mars? But now, with the rise and discovery of all of these exoplanets, the questions about these exoplanets are coming faster than the answers are coming. And now we know of over 5,300 confirmed exoplanets, probably tens of thousands of candidate worlds. Suddenly, trying to understand another planet has become a high priority. And suddenly we realize the gap in our knowledge about Venus. Like the resolution of Magellan, it's right there. Yeah, the resolution of Magellan is terrible, right? Like, I think it's like 100 meters a pixel or something, or 30 meters a pixel. Like, and yet with Mars, we can see things that are a few centimeters across from space. Like, suddenly it's this wonderful planet is right there. We know almost nothing about it. It's time to learn.
It's time to learn. And so I'm sure you're familiar with the missions that NASA selected, and also contributing with Envision. So we're hoping to improve on that, of the insight that we have from Magellan, really do that at much higher resolution, understand the surface a lot better, and probe through with some of in those narrow bands that we can actually look at bulk mineralogy and so forth. So these missions are going to be really exciting. I mean, I think what we're doing here is kind of a step that's going to be critical to understanding Venus, that goes beyond what an orbiter can do. And that's, again, the beauty of having multiple, and I think the need for having multiple assets tackle different parts of the problem, because it is a system. So we'll learn about this. It's going to give us great data. That's going to inform something else, and so on. And it just builds. Yeah. And the more we have there, like with Mars, the quicker we can get a picture of the total system.
Well, Tibor, it's been great to talk to you. If people want to follow your work or follow the research that your group is doing, what's the best place to do that?
That's a wonderful question. So
nobody ever knows the answer to this. It's so funny, dude.
Yeah. Nobody asked me that one.
Google Scholar,
so different parts. Different parts of that we have websites for. So we have a Venus simulation capability where we can simulate the Venus pressure, temperature, and the complex chemistry extended periods of time. So that's what we'll be doing a lot of our testing for our system. So we have a website on that's active, that'll show some of the tests that we've done, some of the results where we've looked at chemical weathering. So there's some of that. I do present at a number of different places. So anybody that looks at Venus science, number of papers. So that's probably the mechanisms that are most common, or they just reach out to me directly. Right. I don't have like a blog or anything like that.
And that's best, I think. Stay off of social media. Just focus on exploring Venus. I think that'll work out for all of us. Well, if and when you do send your spacecraft for months on Venus, would you let us know?
Oh, you bet. Yeah, I'm going to let everybody know about that one.
I'm sure you will. Well, thank you so much for your time, and good luck. It sounds exciting.
Well, thank you. I appreciate the interest, and great talking to you. Take care.
You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the Galaxy Wanderers. And a special thanks to David Giltonan, Maud Sue, George, Jeremy Matter, Jordan Young, Tim Whalen, Dave Varabayoff, Josh Schultz, and M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.